Just a quick video for a review of imaginary and complex numbers. We're going to get into the fundamental theorem of algebra, but for now, in order to really kind of get there, we need to refresh our memories on imaginary numbers. So I'll actually kind of jump ahead a little bit here. A complex number is in the form of a plus bi, right, where a is the real component. Apologize for my handwriting. Bi is the imaginary component. All right. There is a pattern to the powers of the imaginary unit I, all right? So an imaginary number I is defined as being equal to the square root of -1. All right. Fortunately, our calculators can understand that fairly well. You can sort of see it up on the screen. Let me clear that out, though. The I button it's got its very own key. All right. If I type that in, it just tells me I. All right. I is equal to I. Wonderful. But the square root of -1, if I type that in, it'll also tell me I. All right. So it's giving me that relationship. It won't tell me that I is equal to the square root of -1, but we get it one way or the other. So if I want powers of I to the 0th power, because anything to the 0th power is equal to 1. So this is the same as saying I to the 0th, I to the 1st. Stray mark comes up, and I can't figure out how to fix it. I to the 1st is I. Anything to the 1st power is itself. That should make sense. But then you get to I to the 2nd, which is -1. And that's because I to the 2nd power is really I plus I, right? I plus I times I. All right. And since I is equal to the square root of -1, we're really saying radical -1 times radical -1, which would be -1, right? I to the 3rd, I to the 4th, back to a 1, right? So you see we have a cycle, 0, then I, -1, -I, then back to 1, right? And then it would continue that cycle, so we'd end up with I, -1, I, and then back to +1. All right? So the pattern ends up being, if you have a power of 1, that's going to give you a result of I. We'll think of that as kind of the basis of the system. I to the 2nd would be equal to, that was the -1. I to the 3rd is I to the 4th is +1, right? So that's a repeating cycle. We tend to instead of starting off with the I to the 0th power one, we start off with I to the 1st, only because you're not really doing much of anything related to I by raising to the 0th power. Right, so you raise something to the 0th power, whether it's I or a 2, it doesn't make a difference. The result is going to be 1. So that doesn't enhance our knowledge in any way. Right. So if I wanted to find, and I have an example below, but if I wanted to find something like I to the, I'll go 13th power. One thing I could do would be to say I to the 1st, if I know it's a repeating pattern, I to the 1st, 2nd, 3rd, 4th, I to the 5th, 6th, 7th, 8th, 9th, 10th, 11th, 12th, 13th. I to the 13th power is going to be equivalent to I to the 1st power. And we can get that from our calculators, but you'll have to be able to do this by hand at some point for an assessment. All right. Another way of doing it would be to take note of the remainder. If I divide 13 by 4, it's a 4-unit cycle. 4 goes into 13 evenly 3 times, gives me a 12. That's a remainder of 1. All right. So in my cycle here, I'm looking at remainders. Let me see, I might scooch this over a little bit. All right, so my remainder would be 1, 2, 3. That would put it at those locations in the cycle. But the thing is, if it's, for example, I to the, I'll say 24th power, 24 divided by 4 gives me 6. That divides in evenly. My remainder is 0. All right, there's no way that you could have a remainder of 4 if you're dividing by 4. So the remainder for that last one, weirdly enough, would actually just be a 0. All right, this should be underlined. Complex conjugate. If I have, there's a definition for it, but if I have something in the form of a plus bi, then its conjugate would be a minus bi. So these are conjugates of one another. All right. And that's because if you were to multiply them, for example, if I take a plus bi and multiply it by a minus bi, using distributive property, I'd get a squared minus abi plus abi plus b squared I squared, which simplifies down, these cancel, a squared plus b squared I squared. But if I tell you that I squared is equal to -1, a squared plus, sorry, caught myself, these should be minus. Eventually it's going to be plus, so that's why I kind of jumped the gun there. All right, so minus b squared times -1 is going to be a squared plus b squared. All right, so by multiplying by a conjugate, you can get rid of the imaginary component. All right, so when we're looking to simplify expressions, that's oftentimes what we would do. All right, so for something like number 1 at the bottom there, it really is just a matter of taking that 37, divided by 4, goes in, 9 times 4 is 36, remainder 1, so this is equivalent to I to the first power. All right, same idea here, except it's in the bottom of the fraction. I to the 7th, I'd look at that by saying, let me go with an equal sign there. 7 divided by 4 goes in 1 time with a remainder of 3. So I to the 7th is equivalent to I to the 3rd. All right. So I would rewrite this as 1 over I to the 3rd power, knowing that I to the 3rd is equal to -I. Or actually, I don't even have to do that, because if I know that I to the 3rd is equivalent to -I, I could just jump right to that. So I'll write it as or 1 over -I. But sometimes we want to not have i's or radicals in the bottom of a fraction. So I is the square root of -1. So if I rationalize, I could end up with a simpler expression, which would be I over -I squared. I squared is -1. So I'd get a result of I. All right, so if my objective here is to come up with the simplest form of an expression, that would be an option that I could use. It may not be necessary. What I had might have been in simplest form already, but I need to at least make the attempt. This is different from number 3, where I would multiply top and bottom by the conjugate. So I'd get 2 parentheses 1 plus I up top. That's weird. On the bottom, 1 times 1, so we're going to multiply. 1 times 1 is 1. Then my outer plus I, inner minus I squared. So cancel there and there. 2 parentheses 1 plus I over 1 minus -1. I squared is -1. So 2 times 1 plus I over 2 which would simplify down to just 1 plus I. And then the last one, you could actually conjugate or multiply by the conjugate of the numerator or denominator to simplify. And it's just kind of think of it both ways, and whichever one gives you a nicer answer is what you go with. So I could do it as 2 plus 3i over 2 minus 5i, multiply top and bottom by 2 minus 3i. So the conjugate of the numerator. I'm going to move that over a smidge. I'll make a little note. Oh, I don't know what happened there. So numerator. So the conjugate of the numerator, or I could do conjugate of the denominator, which would be, again, 2 plus 3i over 2 minus 5i, multiplied by 2 plus 5i, top and bottom. So when I distribute out the numerators, I would get 4. Outers and inners are cancel, so minus 9i squared. On the bottom, I have to do like actual distributor property. All right, I'll have to show the intermediate. 4 minus 6i minus 10i plus 15i squared. Then I would clean that up. All right, so up top, it's 4 minus 9 times negative 1. On the bottom, 4, I'm going to combine these together, so minus 16i plus 15, instead of I squared, it's going to be negative 1. All right, so up top, 4 plus 9 is 13. On the bottom, I have 4 minus 15 is negative 11, minus 16i. All right, so previously I had i's in the top and bottom. Now I just have it in the bottom, so that's technically simpler than what I had previously. As opposed to rationalizing the denominator with the conjugate. Go purple on the bottom for consistency. So on the top, I'm going to get 4 plus 10i plus 6i plus 15i squared. Simplify that in a sec. But on the bottom, 4 outers and inners cancel, so minus 25i squared. All right, so combining terms, I have 4 plus, these two go together. So 16i plus 15 times negative 1, because again, I squared is negative 1, over 4 minus 25 times negative 1. So I take my 4 and combine it with a negative 15. So that's going to be negative 11 plus 16i over 4 plus 25, which is 29. These two things are equivalent to one another. All right.